Welcome to The Explainer. Today, we're going to talk about a simple but really powerful secret from the world of chemical engineering. It's just a single calculation, but it's one that literally prevents billion-dollar projects from turning into complete disasters. I mean, think about it, right? You would never, ever build a skyscraper without a complete blueprint. But how do you do that for a complex chemical reaction? How can you possibly get that same level of certainty, that guarantee that your whole plan is going to work before you even start? So here's what we're going to do. First, we'll get a handle on the huge question engineers have to answer. Then, we'll dig into the powerful method they use to find that certainty. And we'll even walk through a real-world case study to see why, believe it or not, the number 0 can actually mean everything. Okay, so this is the absolute core of the challenge. Before anyone spends a single dollar, before a single piece of equipment is ordered, an engineer has to face this one really make-or-break question. Is this puzzle I'm looking at even solvable? And it really just boils down to a type of accounting. It's like you're balancing a ledger. On one side, you list everything you don't know, all your unknowns, stuff like temperatures, pressures, flow rates. And on the other side, you list everything you do know, every single piece of solid information you have. So the big question is, how do they actually do this balancing act? Well, they use this incredible tool called degrees of freedom analysis, or DOF for short. Think of it as the engineer's formal, systematic way to find absolute certainty. What it does, in simple terms, is give the engineer a clear verdict. It's like it's answering 3 critical questions for you. 1, is this problem solvable as is? 2, do I need to go find more data? Or 3, and this is the scary one, is there some kind of conflicting information here that makes a solution totally impossible? And the process itself, it's actually surprisingly simple. You just follow these 3 steps. First, you count up all your unknowns. Second, you count up your equations, which are basically just all your pieces of known information. And finally, you just subtract one from the other. That one little number you get at the end, it brings an amazing amount of clarity to some seriously complex problems. Now, here's where it gets really interesting. Engineers actually have a couple of different ways to do this accounting. So let's take a look at the 2 main paths they can take to get to the same answer. You can almost think of it like 2 different detectives trying to solve the same crime. The atomic species method, that's like using fingerprints. Atoms are always conserved, they never lie, so this method is rock solid, super reliable. The other one, the extent of reaction method, is more like using witness statements. It's incredibly powerful if you have all the witness accounts, meaning you know all the reactions happening, but if you're missing even one, it can fall apart. The cool thing is, both can get you to the right answer. Okay, enough with the theory. Let's actually put this into practice. We're going to use a classic chemical engineering problem, the combustion of methane. So what's happening is, inside our reactor, we're burning methane. But the thing is, it's not a totally perfect, clean combustion. Some of that methane is turning into carbon monoxide, CO. The rest of it is turning into carbon dioxide, or CO2, and, of course, water. All right, so here's our setup. We know exactly what mix of gases is going in. And we also have a key piece of info. We know that 90% of the methane gets used up inside the reactor. But what's coming out? Well, that's a mix of stuff, and there are 5 different flow rates that we just don't know. So right there, those are our 5 big unknowns. Okay, let's do the math using that atomic species method. We start with our 5 unknowns. Now let's start subtracting all the things we do know. We've got 3 atomic balances, 1 for carbon, 1 for hydrogen, and 1 for oxygen. We also have a balance for nitrogen, since it's just passing through without reacting. And finally, we have that other piece of information we were given, that 90% conversion of the methane. So that's 5 knowns to count against our unknowns. So you take your 5 unknowns, you subtract those 5 pieces of solid information, and what do you get? You get 0. And that, right there, is the magic number. It's exactly what every engineer hopes to see. Now, this is the really crucial part. 0 doesn't mean nothing. In the world of degrees of freedom, 0 means everything. It means your problem is uniquely determined. It means you have this perfect balance. You have exactly enough information to solve the entire puzzle. It's solvable. And look, this isn't just some clever academic exercise or math trick. This one single number has huge, real-world implications for how we actually design and build things. Getting a degrees of freedom of 0? That's the ultimate green light. It gives you the certainty you need, confirming your design is actually sound.
It creates efficiency because it stops you from wasting a ton of time and money on a problem that was never solvable in the first place. And crucially, it ensures safety because it makes a complex, potentially dangerous process predictable and well-defined. I mean, it's really a cornerstone of modern process design.
So at the end of the day, what this simple little accounting method does is pretty profound. It transforms a total mess of ambiguity into pure clarity. It takes what seems like an impossible chemical mystery and turns it into a solvable, totally manageable engineering problem. And that's really the big idea here, isn't it? It's more than just math. It's a disciplined way of thinking, of carefully balancing what you know against what you don't. And it really makes you wonder, right? What other huge complex systems out there, maybe in our economy or with the environment, maybe even in our own lives, could benefit from this kind of blueprint check? What could we solve if we just stopped first and asked, do we even have enough information to solve this?